Who's ready for a test? I know I reviewed once already, but I'm just going to devote another day to review. I mean, what's it going to hurt? So, good morning, Chad. So let's start off with, these are the same slides as before, but I'm going to do some examples and stuff too. So start off with what we, I think, had at the last time and didn't really get to, Faraday's Law of Induction. So at its essence, what does Faraday's Law of Induction tell you? I mean, what is it basically saying?
Change magnetic flux over time creates an EMF.
That's perfect. That's exactly what it tells you. So anything that changes the flux will create an EMF. What is the magnetic flux? It is a dot product.
So, I want to say it's DL dot D.
That's actually circulation.
Oh.
And Nathan pointed out, I didn't even change it. He pointed out that I don't have it quite written right on the test. I have it written for a closed surface. But we're not using closed surfaces with Faraday's Law of Induction. We're just taking a surface. Maybe I should go change it. I haven't printed the test yet. We're just taking a surface that is contained by a loop. So if the loop is a circle, it's the area of the circle. If it's a square, it's the area of the square. And so that it shouldn't have, on the equation sheet right now, I have the little circle here. It shouldn't have that because it's not on a closed surface. And then I have also sum of B dot A, I think, for the non-calculus. And once again, it doesn't need to have the sum because we're not doing all the closed surfaces. We're just doing this surface. Now, stepping forward, James Clerk Maxwell took this, and well, not this. He took the Ampere's law, and he said that there's, Ampere's law says that the current going through a region is related to the circulation, the magnetic field dot DL as you go around a loop. So it's another one that has a loop. It's an imaginary loop in Ampere's law, where this is a real one in Faraday's Law of Induction. And he said that, well, a change in electric flux is going to is going to look like a current. And so we had flux for both electric flux and magnetic flux. I don't know why I went a wild stray topic there. I shouldn't have. Coming back to this, the reason I went there was in his calculation for how much current is enclosed by the loop. He said, wait a minute. Nobody says that to calculate the flux, I have to take the flat surface across my shape. You could make any shape surface you want as long as the edges are the boundary of your loop. That's why I went there. But then I realized it's going in a completely different direction. But we tend to do it with the flat surface. That's what we're always going to do in this class, okay? You don't have to worry about, now what surface should I choose? If you're doing this, the magnetic flux or the electric flux, you're just going to take the flat surface going across the boundary, so you completely cover the boundary. Okay, so a change in that flux will produce an EMF. So in this equation, integral B dot dA, what can change? Okay, the dA can change. That's one thing. Okay, you can have the area increase or decrease. What else could change?
Magnetic flux.
Well, the magnetic flux. What could change would change the magnetic flux. So I believe what you meant was the magnetic field.
Yeah.
Yeah. So magnetic field strength could change. Or, one other thing. The orientation, because this is a dot product, the orientation between these two matters. So we've done this a number of different ways. So you could have, for instance, let's say that it's a circular loop. Why circular? Because that's the easiest one for me to think about. Even though it has a pi in there, it's the easiest one because it's only one variable. So if we have a circular loop, then we have, and let's do one more thing. This is something that you can generally count on for a general / college physics class. B is uniform over the loop. That means the magnetic field isn't varying as you're going to different parts of the loop. If B is uniform over the loop, then you can simplify B dot dA is equal to B dA cosine theta. And so that means that the flux
The cosine theta is meant to be on the side.
Okay, so the cosine theta and the B, if it's uniform, those are constants with regard to our area. They may not be constant in time, but they're constants with regard to the area. So I think that's what you said, right, Michael? That I can move those outside the integral now? Oops, that's a theta, not an A. But then what is integral of dA by definition? A. So you can take it, for anything we're doing in this class, the flux is going to be BA cosine theta. There are situations where it doesn't have to be that. But for this class, we're going to take a uniform magnetic field over the range of the area. And so it will, without having to do any calculus, become this. So while I have the equations there, remember I said I wasn't really concerned about them not being quite accurate. The reason is because you're just going to use this. And so with that flux, then we have to look at what can change again. We could have magnetic field change, what Michael said. We could have the area change, which I think is what you said. And we could have the orientation change, which is what Chad said. Any one of those is going to induce an EMF. And so things I could give you with this regard would be, let's suppose, well, the one that was on the worksheet. The one that was on the worksheet, you have the angle changing because it was an electric generator. Now, for people in Physics 152, they just take the answer that we get from our calculus. For you guys, you should be able to do the calculus. So if it's rotating, so for a generator, wow, I missed a syllable. I may have an E where I should have it. I think that's right. Let's not worry about it. Yeah. For a generator, B and A are constant, but theta is equal to omega t. And so for a generator, I took the constant stuff out of that derivative, and we have to do that derivative cosine omega t. Derivative cosine omega t is going to be minus omega sine omega t. So a minus and a minus makes it a plus. So this equation is shown on the equation sheet, but you should be able to go through and get there. So Nathan and I were going over that problem on the worksheet today, and he's like, when I did this before in the homework problem, I did it a different way that was easier. He did it using this equation, whereas I was telling him to do it using Faraday's law of induction, doing that derivative. Well, that's one thing that can change. That's for a generator. What's another thing that could change? We've talked about them all. Just throw one out.
The area.
Okay, the area. So let's say that I have, suppose theta and B are constant, and R is equal to, and I'm going to put E plus FT. So the radius is changing with time. I need to insert a page, sorry. Insert 2 pages. I'm sure I won't use them both, but if I do. Okay, if B and theta are constant and R is changing with time, then what am I going to have for the induced EMF?
Should be negative NB cosine omega t.
Well, cosine theta, because theta is constant.
Cosine theta. Over dt? No. D over dt.
And what's going to go here?
Is it A?
Yes, which is pi r squared. That's a pi r squared written at the bottom of the screen. I'll try the pi again. Well, using there's more than one way to do this, but I'm going to do this just using the chain rule. Equals minus NB cosine theta, the part that was out there already. Pi is a constant, so pi comes out. The derivative of r squared with respect to time is going to be 2r dr dt. So now I have to do that derivative of r. What's the derivative of my r here?
Of 2 O.
The single derivative of this right here.
It would just be T. No, I mean F, right? Yeah.
It'd just be f. And so I would have here, for this specific case, that would be my equation now for the induced voltage. Got a little harder there because we had r squared and so on. But in terms of process, we were still just taking the derivative of the flux. It was just a different thing that had changed in the flux. And finally, this is the hardest of the 3 cases, I suppose, because, well, no, it's not any harder. The last case could be the magnetic field changing with time. And once again, you can have the magnetic field changing with some gnarly equation. And you would just have to take the derivative. So that's how Faraday's law of induction, I put in those extra 2 pages, and you know how many of them I used? 0, because I stayed on this page.
Good space plan.
Thank you. So that's how Faraday's law of induction could appear on the test. If it's going to appear on the test for the calculus version, you're going to have to do one of the 2 things I did, or the third one, which would be if the magnetic field is a function of time. Chat.
Okay, so then you just take the derivative of B, the magnetic field.
Yeah. So let's just do an example. So final case. If A and theta are constant and B is equal to, let's say, E plus GT plus HT cubed. bring out the two constant things. And so I just have to go ahead and do that. In this case, that would be G plus 3HT squared.
So those are the three scenarios.
Those are the three scenarios. A question about how any of those three play out. Have some confidence?
So basically, you just take that equation and then you do the derivative.
Yeah, we take this, and you're just going to plug in this phi, and then you take the derivative. And I'm not going to make two things time dependent. Only one would be time dependent. All good? Okay, let's go to the next. Transient circuits. Trace is shaking his head.
This one I do not like at all.
This is the one he hopes doesn't show up.
Yeah.
So starting with transient, what does it mean to be transient? Let's say you find out that Richard Webb is transient. What does that mean?
You move around a lot.
Move around a lot. Don't have a place to call home, right? A transient circuit is moving about, but it's not exactly the same as what Trey said when we talk about the circuit, because transient doesn't imply homeless. It means it's going from one state, or one home, to another state. So it's only doing a process. So our transient circuits are always going to have a starting condition and an ending condition, and we're going to calculate how it goes between them. And if we do a transient circuit problem, you only have two. Now, I looked at my organization last time I went over this, and I did a little circle on the page in my math, which was a little unfortunate. You're only going to have two possible cases. One that has a resistor and a capacitor, and then the rest of the circuit could look different. You could have, like a switch that goes. Also, last time I did this, I had my power supply with positive on both sides. That was a mistake. This would be an example where you would have, for instance, two different power supplies, and it switches from one power supply to the other. Right? That's a little different than what we did before, but all it's doing is changing the starting and ending conditions in the rest of it. And since we're not an electric circuits class, we keep it fairly simple. We just have one capacitor, one resistor. If you take the electric circuits class, you'll have situations where there's like 7 resistors in there and 2 capacitors, and you got to figure out how it works. It gets a little more complicated. So that's case 1 that you could have. Case 2 that you would have would be having, well, let's do this again, a resistor and inductor this time. And then again, we're going to have some switching that goes on to change between circuits. And so I'm just going to draw this one like this. So now my switch can go from there. Whoops. What's wrong with what I just drew? Actually, I did it wrong here too. It needs to be going like that. It's pivoting on the wrong axis there. I need to keep my capacitor or inductor in my circuit when I flip the switch. What I was doing, the way I had drawn the first time, I would just connect the 2 power supplies together when I flipped the switch. That wasn't the goal. So that's the second case you could have for this. In both cases, you want to take what, let me just write these down. So the first thing you do is find the current and voltage immediately after the switch is flipped. Immediately after, because that's your starting condition for your transient case. Now, if you look at these equations at the top, if you have an inductor, because an inductor has a voltage that's proportional to the rate at which the current is changing, the voltage has to be finite. You're not going to have an infinite voltage across it, which means that your current in the inductor has to not change discontinuously. It has to be continuous, which means when you flip the switch, the current can't instantly jump. So the current you had just before you flip the switch is going to be the current you had after you flip the switch. So if it's the inductor case, which is my lower picture here, and so I'm going to write this inside, current initial equals current before switch flipped. Because the current can't jump discontinuously. So you find the initial current by finding the current that you have in the steady state before you flip the switch. Now, if we look at the capacitor, what cannot jump for a capacitor?
Well, just common sense would say that, like, the stored charge wouldn't change.
Okay, the stored charge cannot change in an instant. And since the voltage is proportional to the stored charge, remember V is equal, or Q is equal to VC, then the voltage can't jump discontinuously. So for this one, the voltage so you find the voltage if it's a capacitor or the current if it's an inductor. And once you find that, then you can find what the voltage is by looking at the complete circuit. So those are important keys for finding the I and V immediately after the switch. You find one of them from what it was before the switch, and then you put that into a Kirchhoff's voltage law equation. So I called that step one. I should have said step one. Okay, call that step. Yeah, I'll call it step one and put down here step 0. So you make a KVL equation for the loop after the switch was flipped. So let's do that for each one. So for this upper one, after the switch is flipped, you're going to have E1 connected, right? And so if I make a Kirchhoff's voltage law equation, I'm going to start here and go up E1. Have my current like that. We use the same sign convention for capacitors and inductors as we do for resistors. And so I have E1 minus, I'm going to put V sub R, the voltage drop across the resistor, minus voltage drop across the capacitor equals 0. I didn't use Ohm's law or those equations. I just put it in as VR and VC. That's not going to help me much. But note that VR is equal to IRR, that the current times the resistance. There's only one current here because there's only one loop. And so I can substitute, equals, minus IR for the voltage across the resistor. And then I don't have that kind of substitution, right? I just have VC. And now you're all, wait a minute. I still have two variables, or you should be, wait a minute, there's two variables. There's VC and there's I in that equation. And so the last step is using this relationship to replace the I. So there I have my Kirchhoff's voltage law, my loop equation for the RC circuit. And now I take this and I'm like, well, what do I want to do? What do I want to solve for? What do I want to solve for with this equation?
E1.
Okay, I want to, not for E1. E1's a constant. E1's going to be a given.
So that would be VC.
I want to solve for VC as a function of time. So I have two variables here, VC and time. Well, what I'm going to have to do then is separate variables. Question.
Is that an I or is it a C? After the E1, it's the E1.
This is a C right here.
No, before that.
No.
E1 minus that.
That's a C.
Okay.
That's this C here.
Okay.
It might have looked more consistency if I wrote it that way. So now I need to separate variables. Well, let's go back to the preceding page that we didn't use. Separate variables and integrate. That's what we do with this kind of differential equation. Remember, you guys did have some differential equation stuff in your calculus classes. You haven't taken differential equations yet, but you've had this level. So we have to separate variables. Let's make sure it's real clear. What are the two variables? And T. VC and T. So I need, and how can I tell I have a DVC and I have a DT? So I need to get those on opposite sides of the equation. So I need to start rearranging. So I am first going to move this term by itself on the other side of the equation, the one that has the derivative. So I'm going to have E1 minus V2 equals RC dV, or R, it's VC, dt. Now I note that I have a VC here and here, and I have a DT here. I need my D's to be in numerator positions. So I'm going to have to cross multiply everything by DT to get it into the numerator position. And so I'm going to have DT is equal to RC dVC. Well, I still have VC on both sides of the equations. And so I need to move the VC over so it's on the same side as the DVC. And the only way to do that is to divide the entire thing in parentheses there. And so I divide the entire thing that's in parentheses, and I have that. Now there's one more thing that we usually do, and that one last thing that we usually do is we will divide both sides by minus RC.
Why minus R?
The minus sign is it's not necessary. but it's going to make it so I have a plus VC in the denominator instead of a minus VC in the denominator. So if you divide by RC, you don't even have to divide by RC. It's just a common thing. So what I have now is minus 1 over RC dt equals dVC over VC minus E1. Now I integrate both sides from voltage C initial to voltage C final, and time initial equals 0 because we arbitrarily set the time we flip the switch to 0, and time final. And we integrate. So what's the integral of the left-hand side here?
One over OC. T final. Minus T initial.
Yeah. T final minus T initial, which is 0, so I didn't put the minus 0. So the left side was minus T final over RC. The right side, if you are me, you do a U substitution. You say U is equal to VC minus epsilon 1. Which means du is equal to dVC. I divided by the minus, so I would have du equals dVC instead of minus dVC. That's the only difference it made. So it's not significant. And then when you have the integral of du over u, what's the integral of du over u?
U will be squared. Wait, oh.
It's the one that's not like the rest.
Yeah.
It's the one that's natural log of u. So the right-hand side of this is going to be natural log of u final. Well, since u is VC minus E1, that's going to be VC final minus E1 over u initial, which should be V initial minus E1. And now we're almost done. Because what are we trying to solve for?
VC.
Yeah, VC. Just making sure that we remember that. I asked initially. Let me drop off the finals now that we're out of the integral. And then solving this for VC, I have to do the inverse function of natural log, which is exponential. So E, and I have e to the natural log of this stuff is just going to be so to solve that for VC, I have to multiply both sides by the thing that's in the denominator here. So I'll have and then, of course, you add epsilon 1. Oh, I forgot something very important there. It's kind of important. So I have to add E1 to both sides, and I have and so here I've solved for this specific circuit. And note that I need to have the initial voltage, and we had our condition for this one was the initial voltage is the voltage you had before we flipped the switch. So we just look at before we flip the switch, if it's been sitting there for a very long time, the capacitor will be charged so that we have V initial is equal to E2. Right, it's fully charged because E2 is connected to it. And when you get to the point where there's no current flowing, that means that the voltage across the resistor is 0, hence they're equal. And so I could put in here now, because I know that VC0 is E2, then I have voltage across the capacitor is E1 plus E2 minus E1, E minus T over RC. Now, I went through this a lot slower than you could do, because I wanted to make sure we explained everything and talked our way through how the process works. But the keys here were finding my 0th step is finding the Kirchhoff's voltage law equation. My first step is finding the initial voltage. And then I took that Kirchhoff's voltage law equation and I solved it using calculus. It was a little bit distressing. That's probably why Trace is hoping that that's not in the test. Any questions about how that works?
Okay, so
You guys didn't see Chad's face. It was a little fun. Go ahead, Michael.
So how about those first two equations? Are they just like, can you explain that?
Okay, so the first equation, you're talking about E1 minus VR minus VC equals 0. That's just using Kirchhoff's voltage law.
Okay.
Right, so I did the voltage rise going through E1, then the voltage drop across the
And that's just
resistor, the voltage drop across the capacitor. Yeah.
Okay.
So that's where I got the first equation. That's where you start. And then the second line, I used Ohm's law to replace VR with IR.
Okay.
And then the third line, I replaced I with the box for a capacitor I is equal to CZVDT.
Okay.
And so I did my steps separately there to make sure we can account for the steps. And so now when I got to that third line, this is where I switched pages, but now I have a differential equation with dV, CVT, and VC. So two variables, VC and T, and then we have to separate the variables again. And I say it like that part's the easy part, but I'm guessing it's not the easy part for you guys. Okay?
Yeah, can you explain how you went from the second to third equation?
Yes. So going from the second equation to the third equation, okay, this R, I put the R first and I put I second. So I'll put a box here around the I.
Oh, yeah, I see.
I used this equation to the replacement. I know you said you see it, but I can't stop mid-sentence here and mid-thought. So, doable, right? And if a question like this comes up on the test, you're not going to simply put the reason I said find the initial, you find the initial and the final values, and there's always the same equations that you end up with. You always end up, wow, I used all of that page. You always end up with V is equal to the, what is it? You always end up with that equation. And likewise for current. You always have that. So notice at time equals 0, you're going to have V initial minus V final plus V final, which is V initial. As time approaches infinity, you have 0 plus V final. It's always going to have that form. And so like when you take a circuits class, you learn to do what I said, find the initial condition, find the final condition, put them in. The only difficult part then is finding what tau is. What did we find for tau here? We found that tau was RC. Now, if you go back to the lecture before break, Nate, we did this lower circuit for that one, or something like that, something that was an inductor and a resistor. And with the inductor, it turns out that tau is equal to, I think it was L over R. I would have to actually go through it again. It's on the equation sheet. But for the calculus-based physics class, if you have a question, you would need to show how you did your calculus. Not say, well, here's the result that's been found. We good on that? All right. Ampere's law. Ampere's law is like Gauss's law because we're going to look for symmetries if we're going to use this law. So look for symmetries. We only have two symmetries that we're going to use Ampere's law with. An infinite straight wire or an infinite, of course there's no infinite, solenoid. Those are the only two situations we use it for. So if it's an infinite straight wire, it has a very nice symmetry. That is, for a straight wire, we know magnetic fields always form loops. Magnetic fields can't start somewhere, they just have to continue. And so the only geometry that fits with the straight wire is doing circles around it. And then using our right-hand rule, we know the circle, if the current's going up, the circle's going like this, if the current's going down, the circle's going like that. And so we use a circle for calculational purposes, just like with Gauss's law. Gauss's law, we had an imaginary surface that we calculated on. For Ampere's law, we have an imaginary loop that we calculate on. And so we have to calculate this circulation, the integral over the closed loops, this little circle means closed loop, of B dot dl. Well, given our geometry for the wire, if the magnetic field is going in a circle and my shape is a circle, then B is always going to be parallel to dl. And so B dot dl would just be B times dl, because they're always parallel. And secondly, with my circle concentric on the wire, the magnetic field can't change on that circle. Right? What's the difference in standing a meter away here and standing a meter away here? It's going to look the same. The only thing that would make it different is if I was closer or farther. But the circle is constant distance, so the magnetic field has to be constant magnitude. Which means the integral of B dot dl becomes B times dl, or integral of B times dl, but B is constant, so that becomes B times the integral of dl. And now we've gotten trivial. dl is the length as I go around the circle. So if I integrate the length around the circle, I just get the length. Right? Integrate dl. I'll just get the length. And for a circle, what do we call the length? Circumference. And so for the case of the infinite straight wire, integral of B dot dl simplifies to B times 2 pi r. You would have to go through and explain those processes. You can't just say integral of B dot dl is equal to B times 2 pi r. You know, for all I know, you just memorize that. Now, is that flip it up?
It's not off. It's actually 5 coffee into
I need to stop it. That I was thinking of. The one with the nickel bus. Completely relevant to the test.
Exactly.
So you do the left side, you find the circulation. Then the right side, mu naught times the current enclosed. The current enclosed is the current that passes through your imaginary loop. And this is the one where Clerk Maxwell said, okay, so what defines going through my loop? I have a loop like this. Most people say anything that's crossing between my fingers goes through. But he said, I can make it so I have a surface like this, and something comes up here and stops, then nothing went through my loop. Right? That's where Clerk Maxwell got his displacement current idea from. For you and me, and everyone else. We are just going to say, close the surface between the imaginary loop. Any wire that goes through there, we add its current to get our total current. Right, so it's not a hard calculation. So once you find the current enclosed, then you set the circulation equal to mu naught times current enclosed. And once you set these two equal to each other, then you can solve for whatever the problem is asking you to solve for. So that's Ampere's law for the long infinite wire. Long infinite. I guess that was not what I meant to say. Long and infinite would kind of be implied. The infinite straight wire would be the correct term. And what makes a wire infinite? If the length from where you are to the closest end of the wire is very large compared to how far away you are from the wire, then we're in the limit of an infinite straight wire. The second case where we did this was for the solenoid. And I know I've done all hand waving on the first case. Does anyone have questions about that first case at all? Trace.
So after we find B.dl,
Yes.
we then take B times L equals mu naught, and then make that compared to the second equation?
Okay, so we find, right, we completely ignored this part. This is just the definition of what current is.
Oh, okay. That's
So we do this part, we find, for a long infinite wire, integral of B.dl became B times 2 pi r.
Yeah.
And then on this side, we find what the current enclosed is. And for a typical, if it's a single wire, the current enclosed is the I of that wire. And then we set the two sides equal to each other.
okay.
And then what we traditionally do is we solve for, well, what is B? If B 2 pi r is equal to mu naught I,
Okay.
and you divide by 2 pi r, you have, hey, B equal to mu naught I over 2 pi r.
Get that answer my question.
Okay, check.
mu that's a constant.
Yes, this is the permeability of free space. It's essentially how magnetizable a vacuum is. And if you have something that's not free space, then you replace that mu naught with a mu, because this is specific to vacuum. Air, for our purposes, is equivalent to vacuum, so we just use mu naught. Okay, for the solenoid is harder in theory. And so I tell you what shape we use because otherwise you might not have gotten it. So we use a shape that's approaching infinity away from the coil. So that means the magnetic field at the end of the loop is, well, let's say approaching zero. And if we were to draw the magnetic field lines for a solenoid, we know that they have to form loops. And based on the symmetry, if this is an infinite solenoid, I know you can laugh at the word infinite, but if it's an infinite solenoid, then the magnetic fields are going to be perpendicular to the sides of that rectangle. So while the magnetic field is not zero there, the B.dl on that surface is zero because B is perpendicular to dl. So the circulation on the vertical sides, both sides of course are the same, is going to be zero. And the circulation for the end is zero because we've gone so far away. And then what we're left with is the circulation for the inside portion. I can't use that color there. The circulation for this inside portion, let's say that that's a length A across, is going to be the magnetic field inside times A. Because it's B is parallel to the length. So it's just B times A is the integral of B.dl. So now we found the total circulation. It's Bn times A plus 0 plus 0 plus 0. So that was step one, find the circulation. What was step two? Find I enclosed first, then plug those two back in. And I always have to emphasize, because people forget, you find both sides and then do the equality. Don't find one side and say, now I found the other. So I look at here, how much current is enclosed by my loop. If current I is running through my coil, how much current is enclosed?
how much I goes through.
Well, it's not just I, though. It's how much I goes through, yes, but it's not just I, because I is the current going through each loop. And there's more than one loop, potentially, inside of my...
Times the number of loops.
Okay, so it's going to be I times the number of loops that are enclosed by my box, by my calculation loop. And so now I need to find a way to find how many loops are enclosed. And the way we find how many loops are enclosed is actually pretty logical. We have n loops in a distance of L. And so if I take n loops in a distance of L and I multiply it by the length A, that's going to tell me the proportion of the total loops that are inside. And so the number of proportions, telling me how many loops are enclosed by my box. And so that's the number of loops enclosed, and following what Michael said, I take that number of loops enclosed and multiply it by, can you guys read this color?
Yeah.
Okay. And I multiply it by the current going through one loop, and that's the total current enclosed. So now I have all of my pieces squared away, and now I put them into Ampere's law. So I have Bn times A, that's my circulation. That's the left-hand side of the equation right there. Oh, it says right above it, circulation. I don't need to write it again. Circulation. So Bn times A is equal to mu watt times the current enclosed, which is N over LA times I. And notice my A's cancel. Super important, because what did A represent physically? Nothing. A was just for our calculational purposes how wide we're making our box. If our answer depended on A, we know we made a mistake, because that was just an arbitrary decision of how wide to make our little box for doing the calculation.
Do they cancel out?
So the A cancels out, and I have the magnetic field inside is equal to mu watt N over L I. So there's only two cases that we're going to use Ampere's law for, potentially. The infinite straight wire and the infinite solenoid. And I hand waved through one and I did the other one here. And I'm 4 minutes over. I was thinking I've gone pretty long. Well, we reviewed 3 of the 4 things today. We reviewed all 4 of them 2 Tuesdays ago. So hopefully we're very prepared. The last thing was the Biot-Savart law.
Before you close that out,
Yeah.
could you just write down the equation for an infinite life? Because you didn't actually